Okay. Assalamualaikum warahmatullahi wabarakatuh. Hello, my friends in semester Mastukan. We are from group 5, which consists of me, Rachma Nur Asih, and Rakha Praditya Wibowo. We will explain about intervals. Next. This is the materials we want to explain. There are introduction, characterization of intervals, nested intervals, the uncountability of real numbers, binary representations, decimal representations, and periodic decimals, and Cantor's second proof. For introduction, the order relations on real numbers determines a natural collection of subsets called intervals. If A be element of R satisfy A less than B, then the open interval determined by A and B is the set of open interval is equal by definition x element of real numbers such that x greater than A but less than B. The points A and B are called the endpoints of the interval. However, the endpoints are not included in an open interval. If both endpoints are adjoint to this open interval, then we obtain the closed interval determined by A and B, namely the set of closed interval AB equal by definition x is the element of real numbers such that x greater than or equals of A but less than or equals B. The two half open or half closed intervals determined by A and B are half open A from A to B, which includes the endpoint A, and half closed from A to B, which includes the endpoint B. Each of these four intervals is bounded and has length defined by B minus A. If A equals B, the corresponding open interval is the empty set AA equals empty, whereas the corresponding closed interval is the singleton set AA equals to set A. There are five types of unbounded intervals for which the symbol infinity and negative infinity are used as notational convenience in place of the endpoints. The infinite open interval are the sets of the form the open interval from A to infinity equal by definition x element of real numbers such that x greater than A, and the open interval from negative infinity to B is equal by definition x of element of real numbers such that x less than B. Characterization of intervals. There is characterization theorem. If S is a subset of real numbers that contains at least 2 points and has the property if x, y element S and x less than y, then the closed interval from x to y is the subset of S. Then if S is an interval. Proof. There are four cases to consider. First, S is bounded. Second, S is bounded above but not below. The third, S is bounded below but not above. And the fourth, S is neither bounded above nor below. For the case 1, let A equal by definition infimum S and B equal by definition supremum S. Then S is the subset of the closed interval from A to B, and we will show that the open interval from A to B is the subset of S. If Z is greater than A but less than B, then Z is not a lower bound of S, so there exists X element of S with X less than Z. Also, is not an upper bound of S, so there exists Y element of S with Z less than Y. Therefore, Z is the element of the closed interval from X to Y, so property 1 implies that Z element of S. Since, since Z is an arbitrary element of the open interval from A to B, we conclude that the open interval of A to from A to B is the element of S. Now, if A element S and B element of S, then S is equal to the closed interval from A to B. If A is not the element of S and B is not the element of S, then S is equal to the open interval from A to B. The other possibilities lead to either S equals the half closed interval from A to B, or S equal to half open from A to B. For case 2, let B is equal to by definition supremum S. Then S is the subset of half closed negative infinity B, and we will show that the open interval from negative infinity to B is the subset of S. For if Z less than B, then there exists XY element S, such that Z is the element of the closed interval from X to Y is the subset of S. Therefore, the open interval from negative infinity to B is the subset of S. If B element of S, then S is equal to the half-closed interval from negative infinity to B. And if B is not the element of S, then S is equal to the open interval from negative infinity to B. For the case 3, let A is equal by definition of infimum S. Then S is the subset of half-open interval from A to infinity. And we will show that the open interval from A to infinity is the subset of S. For if A less than B, then there exists XY element of S such that Z element of the closed interval from X to Y is the subset of S. Therefore, the open interval from A to infinity is the subset of S. If A element S, then S is equal to the half open interval from A to infinity, and if A is not equal S, then S is the open interval from A to infinity. For case 4 is left for an exercise. And then is nested if the following chain of inclusions hold I1 superset I2 superset In superset In plus 1. This is the figure of nested interval. It is important to realize that in general, a nested sequence of intervals need not have a common point. However, it is an important property of real numbers that every nested sequence of closed bounded intervals does have a common point. And then there is nested intervals property. If In equals to the closed interval from An to Bn, and is the element of natural numbers, is a nested sequence of closed bounded intervals. then there exists a number C element of real numbers such that E such that C is the element of In for all n element natural numbers. For the proof, since the intervals are nested, we have In is the subset of I1 for all n element of natural numbers, so that An is less than or equals B1 for all n is the element of natural numbers. Hence, the non-empty sets An such that n is the element of natural numbers is bounded above, and we let C be its supremum. Clearly, An is less than or equals C for all n element of natural numbers. We claim also that C is the element of that C is less than or equals of Pn for all n. This is established by showing that for any particular n, the number Pn is an upper bound for the set Ak such that k element of natural numbers. We consider two cases. The first case is if n less than or equals k, then since In is superset of Ik, we have Bk is greater than or equals Ak but less than or equals Bn. And the second case, if k less than n, then since Ik superset of In, we have An is greater than or equals Ak but less than or equals Bn. Thus we conclude that Ak is less than or equals Bn for all k, so that Bn is an upper bound of the set Ak such that k element of natural numbers. Hence C is less than or equals Bn for each n element of natural numbers. Since C is greater than or equals Ak but less than or equals Bn for all n, we have C is the element of In for all n of element natural numbers. This is the figure of the case 2. And then we have theorem. If In is equal by definition, the set A and Bn, n element of natural numbers, is a nested sequence of closed bounded intervals such that the lines Bn minus An of In satisfy infimum Bn minus An such that n element of natural numbers equals 0. Then the number C contained in In for all n element of natural numbers is unique. For the proof, if eta is equal by definition infimum Pn such that n element of natural numbers, then an argument similar to the proof of nested intervals property can be used to show that An is less than or equals eta for all n, and hence that C is less than or equals of eta. In fact, it is an exercise to show that x element of In for all n element of natural numbers, if only if x is greater than or equals C, but less than or equals eta. If we have infimum Pn minus An such that n is the element of natural numbers equals 0, then for any epsilon greater than 0, there exists an n element of natural numbers such that eta minus C is such that 0 less than or equals eta minus C less than or equals Pn minus Am less than epsilon. Since holds for all epsilon less than 0, it follows from theorem 2.1.9 if A element of real numbers is such that A greater than or equals 0 but less than epsilon for every epsilon greater than 0, then A equals 0. That eta is that eta minus C is equal 0. Therefore, we conclude that C equals eta is the only point that belongs to In for every n element of natural numbers. The next material is the uncountability of real numbers. We have theorem the set R of real numbers is not countable. For the proof, we will prove that the unit interval I is equal by definition uh, the closed interval from 0 to 1 is an uncountable set. This implies that the set R is an uncountable set, for if R were countable, then the subset I would also be countable. See theorem 1.3.9, option A. That is, suppose that S and T are sets, then T is the subset of S. If S is a countable set, then T is a countable set. The proof is by contradiction. If we assume that I is countable, then we can enumerate the set as I equals x1, x2 until xn. We first select a closed subinterval I1 of I such that x1 is not the element of I1. Then select a closed subinterval I2 of I1 such that x1 element is not the element of I2, and so on. In this way, we obtain non-empty closed interval. I1 is the superset of I2 is the superset of until In, such that In is the subset of I, and Xn is not the element of In for all n. The nested intervals property implies that there exists a point C element of I such that C element of In for all n. Therefore, C is not equal to Xn for all n elements of natural numbers. So the enumeration of I is not a complete listing of the element of I, as claimed. Hence, I is an uncountable set. Then there is binary representation will be explained by Rakha.
The next one will be discussed about binary representation. If X an element of closed interval 0 to 1, we will use a repeat bisection procedure to associate a sequence that is En of zeros and 1 as follows. First, if X doesn't not equal half belongs to the left subinterval of closed interval 0 to half, we take A1 is defined to be equal to 0. If X not equal half belongs to the right subinterval of closed interval half to 1, we take A1 equals to 1. And if X is equal to half, then we may take A1 to be either 0 or 1. In any case, we have X is or between A1 over 2 and A1 plus 1 over 2. Next, we will now bisect the interval of closed interval A1 over 2 to A1 plus 1 over 2. First, if X is not bisection point and belongs to the left subinterval, we take A2 is defined to be equal 0. Second, if X is not bisection point and belongs to the right subinterval, we take A2 is defined to be equal to 1. And last, if X is equal 1 over 4 or X equal 3 over 4, then we take A2 to be either 0 or 1. In any case, we have X is or between A1 over 2 plus A2 over 2 power of 2 and A1 over 2 plus A2 plus 1 over 2 power 2. The continued bisection procedure that if x is not bisection point and belongs to the left subinterval, we take En is defined to be equal 0, and if x is not bisection point and belongs to the right subinterval, we take En is defined to be equal 1. For each n, we have the inequality of x is or between a1 over 2 plus a2 over 2 power 2, so and plus and so on until En over 2 power n, and a1 over 2 plus a2 of per 2 power 2 plus so on until an plus 1 over 2 power n. Next, if x is the bisection point at the nth stage, then x is equal m over 2 power n, with m is odd. In this case, we may choose either the left or the right subinterval. However, once this subinterval is chosen, then all subsequent subintervals in the bisection procedure are determined. To summarize it, if x is an element of closed interval 0 to 1, then there exists a sequence that is an of zeros and ones, such that inequality of this inequality hold for all n element of natural number. In this case, we write x equal 0.a1, a2 continues to an, and so on, and call it a binary representation of x. This representation is unique, except when x equal m over 2 power n for m odd, in which case x has the two representations. That is, x equal 0.a1, a2, so on until en minus 1, 1, 0, 0, 0, and so on, equals 0.a1, a2, until en minus 1, 0, 1, 1, 1, and so on. One ending is zeros, and the other ending is 1. Conversely, each sequence of zeros and ones is binary representation of a unique real number in closed interval 0 to 1. The inequality of following the inequality, determine a closed interval with length 1 over 2 power n, and the subsequence of this and the sequence of this interval is nest. Therefore, theorem on nested interval that we just discussed before implies that there exists a unique real number x satisfy this inequality for every n element of natural number. Consequently, x has the binary representation of 0.a1, a2 continues to en, and so on. The next we will discuss about decimal representation. We're given x an element of closed interval 0 to 1. If we subdivide closed interval 0 to 1 into 10 equal subintervals, then x belongs to a subinterval of closed interval b1 over 10 to b1 plus 1 over 10 for some integer b1 in between 0, 1 until 9. Proceeding as the binary case, we obtain a sequence that's a bn of integers with bn is or between 0 to 9 for all n element of natural number, such that x satisfied of x is or between b1 over 10 plus b2 over 10 power 2, so on until bn over 10 power n, and b1 over 10 plus b2 over 10 power 2, so on until bn plus 1 over 10 power n. In this case, we say that x has a decimal representation given by x is 0.b1, b2, continuously into bn, and so on. If x more than 1, and if b is an element of natural number such that x greater than equal b but less than b minus 1, then x is b point b1, b2, continuously into bn, and so on. The decimal representation of x element of closed interval 0.1 is unique, except when x is a subdivision point at some state, which can be seen to occur when x equal m over 10 power n for some m n if element of natural number, where m is between 1 and 10 power n. When x is a subdivision point at the nth stage, one choice for Bn corresponds to selecting the left subinterval, which causes all subsequent digits to be 9, and the other choice corresponds to selecting the right subinterval, which causes all subsequent digits to be 0. For example, x is equal 1.2, then x is equal 0.4999 so on, and is equal 0.5000 so on. And the other, y equal 38 point over 100 is equal 0.37999 and so on, and is equal to 0.3800 and so on. The next is about the periodic decimals. A decimal b point b1, b2, conditionally to bn and so on is said to be periodic if there exists k n element of n such that bn equals bn plus m for all n is greater than equal k. In this case, the block of digit bk, bk plus 1, and so on until bk plus m minus 1 is repeated once the kth digit is reached. The smallest number m, which is property, is called the period of decimal. For example, 19 over 88 is equal 0.215909090 continuously 90 and so on, as period m equals 2 with repeat block of 90 starting at k equals 4. The terminating decimal is a periodic decimal where the repeat block is simply the digit 0. Here with the assumption of a positive real number is rational if and only if its decimal representation is periodic. To prove it, we suppose that x equals p over q, where p and q is an element of natural number, have no common integer factor. For convenience, we will also suppose that p is between 0 and q. We note that the process of long division of q into p gives the decimal representation of p over q. Each step in the division process produces a remainder that is an integer from 0 to q minus 1. Therefore, after a most q steps, some remainder will occur a second time, and at that point, the digit is the quotient will begin to repeat themselves in circle. Hence, the decimal representation of such a rational number is periodic. Conversely, if a decimal is periodic, then it repeats a rational number. To prove it, we're going to use an example as the best illustration. Suppose that x equals 7.31414 continuously 14. We multiply by a power of 10 to move the decimal point to the first repeating block. Here, obtaining 10x equals 733.1414 so on. We now multiply by a power of 10 to move one block to the left of the decimal point. Here getting 1000x equals 7314.1414 and so on. We now subtract to obtain an integer. Here getting 1000x minus 10x that is equals 7314 minus 73 is equal 702,041, when x equals 7,241 over 990 is a rational number. Last one about the Cantor's second proof, the theorem of the unit interval in the closed interval 0 to 1 is defined to be equal of x number of real number where x is or between 0 and 1 is not countable. To prove it, we're going to use a contradiction. We will use the fact that every real number x, element of closed interval 0 to 1, has a decimal representation x equals 0.b1, b2, b3, and so on, where bi equals 0, 1 until 9. Suppose that there is an enumeration x1, x2, and x3 of all number in closed interval 0 to 1, which we display as x1 equals 0.b11, b12, b13, continuously to b1n, and so on. X2 is 0.b21, b22, b23, continuously into b2n, and so on, and continuously until xn, called 0.bn1, bn2, bn3, continuously into bnn, and so on, and it still continues. We now define a real number y is defined to be equal of 0.y1, y2, y3, continuously into yn, and so on, by setting y1 is defined to be equal to if b11 is greater than equal 5 and y1 is defined to be equal to 7 if b11 is less than 4. In general, we let y, yn is defined to be equal to if bnn is more than equal 5 and 7 if bnn is less than 4. Then y is element of 0 closed interval 0 to 1. Note that the number y is not equal to any of the numbers with two decimal representation, since yn is not equal to 0.9 for all n is element of natural number. Further, since y and xn differ in the nth decimal place, then y is not equal to xn for any n element of natural number. Therefore, y is not included in the enumeration of the closed interval 0 to 1. Is contradict the hypothesis. That's it from our presentation. Thank you for your understanding, and we apologize for any mistake. Wassalamualaikum warahmatullahi wabarakatuh, and good day.